Okay, so this tutorial is just going to be a little quick review on momentum and work energy power. So we're going to start off actually by talking about the force being equal to the rate of change in momentum. And the reason why this is important is because if you rearrange this equation, you get your delta P is equal to F times delta T. So this makes you think about a force versus time graph. And if you were to look at something, let's say like a ball hitting a wall, the force would be a changing force as a function of time. And the reason why we would take a look at this graph is that that area that's enclosed right there, that area is what we call the impulse. So what we end up seeing is that the impulse J is equal to your change in momentum because it's equal to your F times your delta T. And units wise, we have newtons here, we have seconds here, so your units for your impulse is a newton second. We also talked about when we were discussing momentum is conservation of momentum. Now, as an equation, that's m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Now, there's a couple different scenarios where we might need to simplify this a little bit. So first of all, if we're talking about an elastic collision is where kinetic energy, so let's write this down. So elastic is where your kinetic energy is conserved. So we know that energy is always conserved, but it doesn't necessarily have to be kinetic energy. You think about two objects hitting each other, it may be the heat generated in that contact that is going to take away some of its kinetic energy. So energy is still conserved, but not always kinetic. So if we have an elastic collision, what you know is that the kinetic energy is conserved. And why that's important is because then you could set the kinetic energy of the two objects before the collision equal to the kinetic energy of the two objects after the collision. And sometimes that is very useful. The other type of collision that we'll talk about is if it's not elastic, it's inelastic. And there's a very special type of inelastic collision, and that is called a total inelastic collision. And that is where the objects stick together. And when the two objects stick together, that means is that v1 prime is equal to v2 prime, so let's just call it v prime. So if you're looking at the second half of this equation right here, what we can do for a totally inelastic collision, what we can do is we could pull out that v prime, and then we have m1 plus m2. And so that is still going to be equal to your m1 v1 plus m2 v2. The other content that we're going to be just chatting about with, like I said, very briefly, is work. So the definition of work, remember, is a change in total energy. So we calculate work by taking that force that's applied to an object and multiplying it by the displacement that it moves along. And then since work is a scalar and both these are vectors, we need to take into account the cosine of the angle between the force and the displacement vector. So very simple example, we have a block that is on a tabletop and we apply some force at an angle. The angle is relative to the horizontal, and we move the block some distance, I'm just going to do a solid line here, some distance s. So the amount of work done would be the force times that displacement times the cosine of the angle between the displacement vector, which would be along this axis, and then the force vector. Now notice that if the displacement's this way and the force, this is really F cosine of theta, they're along the same direction, so the angle is 0, so then this is 1 and you get a maximum work. You can also reverse that. If, let's say, the box was sliding So we have a sliding block, so its velocity is this way. So its displacement vector would also be that way. But you're applying a force to it in that direction. Then the angle between the force vector and the displacement vector is 180, and the cosine of the angle will be -1. So the way this works out mathematically is that you have negative work, which all that means that is that you're taking some energy away. The last thing that we'll just chat about here is considering your conservation of energy. So when I first introduced this, we did something called the LOL chart. And the reason why this is just really important is it's a way to visually get to visualize how your energy is stored before at one scenario and at some other point in time. So you have the choice of choosing the 2 points of time based on the problem, and it's really just choosing wisely that will help you solve the problem. So let's say I throw a ball up and I give it some initial velocity, and I want to know how high does it go. So what is that maximum height? And so what I can say is that in the beginning it had all kinetic energy, right when I throw it, the instant it leaves the ground, and at the highest point when it stops moving, all of that energy is gravitational potential. So then that's when we did the 1/2 mv squared is equal to your mgh, and notice your m's cancel out, and that h would be equal to v squared over 2g. So that's all for now. Like I said, this is very short. This is just a little overview. If you have any questions, please let me know. All right. Have a good night. Bye-bye.